Hello again. My name is Nicholas Perryman, and this is my test 3 for discrete math. So the problem this time around is to prove that the ceiling of n over m is equal to the floor of n plus m minus 1, all of that over m, and just prove that this is true for all integers n and all positive integers m. So we've got a few relevant properties here. The first two will be the main ones that we look at. So n equals qm plus r, and q equals the floor of n over m. We've also got r equals n mod m, and the floor of x plus n equals the floor of x plus n as just the integer n. So just doing some property manipulation to kind of get a basis. Um, n equals qm plus r. So if we set our domain so that r is greater than or equal to 0 and less than m, so that's the domain for the later, basically. Uh, so if we divide the equation by m, then we'll get n over m equals q plus r over m. And then if we uh, do a ceiling function on both sides of that, and then we kind of apply our domain, then we'll wind up with two different cases. So when r equals 0, then the ceiling of n over m is just going to equal q. And when r is greater than 0, it'll equal q plus 1. Now, going back and looking at the problem, so we've basically got um, the left side of the equation already kind of figured out. And now we need to prove that the right side of the equation is also equal to q or q plus 1. Ideally, both. So if we apply the first property, which is just the substituting for n, then we'll get qm plus r plus m minus 1 over m, and it's the floor of that. So we can simplify just a little bit because the q is multiplied by m, so that can just be pulled out of the fraction and set on its own. Which is nice because when we check the domains, then the fraction will either reduce down to 0 or to 1, um, depending on which set of domains it's based on. And that's uh, reducing based on the floor function. So if r is equal to 0, then the floor of q plus r plus m minus 1 over m is equal to q. And since that equation was already set to be equal to the right side of the equation we're trying to prove, then we have that equals q a few steps removed as long as r equals 0. Now, if r is greater than or equal to 1 or less than m, then we'll wind up with that side of the equation equals q plus 1. And so if you do plug in the r equals 0, if you just want to look at it a little bit more in depth, you'll wind up with the fraction m minus 1 over m, and that is less than 1. So when you do the floor function, that's going to go down to 0. When you do um, are greater than or equal to 1, then the fraction itself is going to be greater than or equal to 1, and in this case, less than 2, because it is still a functional fraction. And due to the domains, it can't be 2 or higher. And therefore, when you apply the floor function to that, it will just be 1. So that's how we get to q plus 1. Now, if we just want to verify that some of these things are still true, then we can just do some algebraic stuff. Just kind of verify that the second property, which just defined what q is true for this equation. And we also apply property 4 in here, which is the floor of x plus n equals the floor of x plus the integer n. So basically what we do is we simplify, well, maybe not simplify the fraction, but we kind of separate the fraction in the floor function. So then we wind up with the n over m plus 1 minus 1 over m. And when we apply the floor function to those individual parts, we'll get the floor of n over m plus 1 minus 1. And the plus 1 minus 1 obviously cancels out. So then we'll just have the floor of n over m, which is the definition of Q. So taking all of that into account, we can determine that if R equals 0, then both sides equal Q, which means that both sides are equal to each other. If R is greater than or equal to 1 and less than M, then both sides equal Q plus 1. So both sides equal each other. And I'm not entirely sure that that's exactly proving it, but that works for me. So thanks for watching.